Before we can construct estimates of the variance of the OLS estimator, we need to know what the overall variance is based on some unknown factors. So we're going to start with the same 4 assumptions as we began with, but we're going to make 2 additional assumptions in order to try and make the maths easier. So there are 2 further assumptions that we're going to make about the observations of x and the error terms. The first is that the x's that we observe we're going to treat as if they're fixed in repeated samples. Now this is a strong assumption. It's much stronger than we'd ever expect to hold in reality, because if you think about what happens when you take a second sample from a population, you're not going to observe the same observations of x again. But by making this assumption, it makes the maths much easier. The 6th assumption is that the variance of the error terms are constant. And again, this is going to make the maths slightly simpler in order to make it easier to understand what's going on. Now, the final thing that we're going to do to try and make our maths a little bit easier is we're going to try and write the OLS estimator as a linear estimator, an estimator that can be written as a linear function of the y's. Now, why will this help us? Well, it will help us just because we then won't have to deal with all of the observations of x's when we are trying to manipulate the estimator. So, how do we go about doing this? Well, we know that the OLS estimator beta1 hat can be written as the sum of the xi minus x bar times by yi over the sum of the x minus x bar squareds. So we could rewrite this as being the sum of the wiyi, where wi is just equal to xi minus x bar over the sum of the x minus x bar squared. Each of the observations of yi is multiplied by xi minus x bar over the sum of the x minus x bar squareds. I'm going to leave this as an exercise for you to do, but if you substitute the data generating process into our estimator, it's possible to show that the OLS estimator can be written as beta1 hat is equal to beta1 plus the sum of the xi minus x bar ui over the sum of the x minus x bar squared. But we've got our wi in here again. The xi minus x bar over the sum of the x minus x bar squared, that is our wi. So we can write that the OLS estimator is equal to beta1 hat, which is equal to beta1 plus the sum of the wi ui's. This is going to be much easier to construct the variance of. So, we want to find the variance of beta1 hat. So we're going to want to find the variance of this expression. So we have that the OLS estimator can be written as beta1 plus the sum of the wi ui's. Now we're making a 5th assumption that the x's are fixed in repeated samples, and that means that we're going to treat the x's as if they are fixed when we're looking at the variation across samples. Now, in order to denote this, we can turn the x's into lowercase x's, and similarly, the wi we're going to turn into a lowercase w, because we're treating those x's as if they are fixed in repeated samples. Now, it's going to make the maths easier, and the reason is that we can treat the x's as fixed with respect to the ui's. We could do the same sort of thing by looking at the law of iterated expectations, but the maths is a little bit more complicated, but we get to exactly the same answer. So, let's try and work through the maths. The variance of beta1 hat is going to be equal to the variance of beta1 plus the sum of the wi ui's. Now we've got the variance of a sum, but the variance of beta1, because beta1 is just a constant, is going to be 0. So the variance of any constant plus a random variable is going to be equal to the variance of that random variable. So we can rewrite this variance as being the variance of the sum of the wi ui's. Now, the variance of any sum is going to be equal to the sum of all of the variance terms plus 2 lots of all of the covariance terms as well. So here we're looking at the variance of the sum of the wi ui's. The wi we're treating as a fixed multiplier. The wi, remember, is that xi minus x bar over the sum of the x minus x bar squared, and we're treating the x's as being fixed in repeated samples. So we're treating them as if they are a fixed multiplier. So we could rewrite this variance of the sum as being wi squared times by the sum of all of those variance terms plus the sum of all of those covariance terms as well. Now, our assumption that the observations are IID Now, the assumption that we made much earlier, that the pairs of observations of x and y are independent and identically distributed, comes into play now. Because the pairs of observations of x and y are independent and identically distributed, it also follows that the ui's are independent and identically distributed. So that will mean that the covariance terms are going to be equal to 0. So these covariance terms are going to disappear from our expression, and we'll just be left with that the variance of beta 1 hat is equal to the sum of wi squared times by the variance of the ui terms. Because remember, the variance of the ui's is assumed to be some constant sigma squared u. So now we can rewrite this expression in terms of the x's. The wi, remember, is equal to xi minus x bar over the sum of the x minus x bar squared. So the wi squared is going to be this wi squared, so it will be xi minus x bar squared divided by the sum of x minus x bar squared all squared. So we can rewrite the variance of the beta 1 hat as being equal to sigma squared u times by the sum of the x minus x bar squared divided by the square of the sum of the x minus x bar squareds. We've got the sum of the x minus x bar squareds divided by the square of the sum of the x minus x bar squareds. So one of those can cancel, leaving us with the variance of beta 1 hat is just equal to the variance of u divided by the sum of the x minus x bar squareds. So far we've shown that the variance of the beta 1 hat is equal to the variance of the error term divided by the sum of the x minus x bar squareds. We've also shown that provided our first two assumptions are true, that the OLS estimator is unbiased, so the expectation of beta 1 hat is equal to beta 1. The final thing that we always want to do when we're carrying out statistical tests is to know what the distribution of the estimator is. And the central limit theorem, just as with the sample mean, will apply for the OLS estimator. The central limit theorem applies such that the OLS estimator will follow an approximately normal distribution, provided you have sufficient observations. Again, more than about 30 observations will do. So we can write that the OLS estimator beta 1 hat will be approximately normally distributed, centered on beta 1, so the expectation of beta 1 hat will be beta 1, with variance equal to the variance of u divided by the sum of the x minus x bar squareds. Now we've made 6 key assumptions here. If any of those assumptions are incorrect, then the distribution of the OLS estimator, the distribution of the beta 1 hats, will be something different. If, for instance, the variance of the ui's is not fixed, then the variance of the OLS estimator won't be this expression. If the observations of x are not exogenous, if the x's themselves are related to the error term, then the OLS estimator won't be unbiased, so the expectation of beta 1 hat won't be equal to beta 1. So in each of these cases, if our assumptions break down, then the distribution will be something different.